And now in this lecture we'll answer two questions. In the first question we'll find out the area of this trapezoid ABCD, and in the second question we'll find out the area of this quadrilateral ABCD using two different methods. So we'll start with the first question. In the drawing we have trapezoid ABCD, and the trapezoid ABCD blocks this circle, or the circle is inscribed by trapezoid ABCD. In addition, you know that side DA is equal to side CB equals to 41 units in its length, and side AB equals to 50 units in its length. Again, our test is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. And again, this is a trapezoid ABCD. Side DC is parallel to side AB, and for that reason, quadrilateral ABCD is a trapezoid. If we define the length of side DC as A and the length of side AB as B, then and the height onto this trapezoid is H, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the height H over 2. And again, the area of trapezoid equals to the sum of its two parallel bases times the height H over 2. The height H must create 90 degrees with the two parallel bases. So, in the first step, we will implement rule 2 in our drawing. We click on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing, we have a circle. This is the common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle, tangent BA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. In our drawing, first of all, we will define the point of tendency of tangent DC with this circle. This point is point E. And we will define the point of tendency of tangent CB with this circle. This point is point F. We will define the point of tendency of tangent DA with this circle. This point is point K. And finally, we will define the point of tendency of tangent AB with this circle. This point is point L. We return to rule 2. According to rule 2, if we focus on this common standpoint point D, from this common standpoint point D, we have two tangents to this circle, tangent DE and tangent DK. And according to rule 2, they are equal to each other. That is to say, DE equals to DK. So if we define the length of tangent DE as A, then the length of tangent DK must be also equal to A, because they are equal to each other according to rule 2. Likewise, we focus on this common standpoint point A. From this common standpoint point A, we have two tangents to this circle, tangent AK and tangent AL. And according to rule 2, they are equal to each other. That is to say, AK equals to AL. So if we define the length of tangent AK as B, then the length of tangent AL must be also equal to B, because they are equal to each other according to rule 2. Likewise, if we focus on this common standpoint point C, from this common standpoint point C, we have two tangents to this circle, tangent CE and tangent CF. And according to rule 2, they are equal to each other. That is to say, CE equals to CF. So if we define the length of tangent CE as C, then the length of tangent CF must be also equal to C, because they are equal to each other according to rule 2. And finally, we focus on this common external point, point B. From the common external point, point B, we have two tangents to this again. Tangent BF and tangent BL. And according to 1, 2, they are equal to each other. That is to say, BF equals to BL. So if we define the length of tangent BF as D, then the length of tangent BL must be also equal to D according to rule 2. So what is the length of side DA plus side CB? And again, what is the length of side DA plus side CB? DA plus CB equals to A plus B plus C plus D. Repeat again. Side DA plus the opposite side CB, the trapezoid ABCD, in total equals to A plus B plus C plus D. What is the length of side DC plus the opposite side AB? So DC plus AB equals to A plus B plus C plus D. Repeat again, if we found out that A and DA plus CB equals to A plus B plus C plus D, and CD plus AB also equals to A plus B plus C plus D, and therefore those two expressions must be equal to each other. That is to say, DA plus CB equals to CD plus AB. So it is known. If we found out that CD plus AB equals to DA, CD plus AB equals to DA plus CB. CD is the missing side, so we leave it as it is, so it is CD plus AB. AB equals to 50 units in its length according to what is given in the question, and it is equals to DA. DA equals to 41 plus CB. CB also equals to 41. So in total, we actually found out that CD plus 50 equals to 41 plus 41. So CD plus 50 equals to 41 plus 41 is 82. So CD plus 50 equals to 82. Here we'll subtract 50 from this equation, and we get that CD equals to 82 minus 50 is 32. So the missing side CD equals to 32 units in its length. This is the missing side CD, this is equals to 32 units in its length. In the next step, we will do a construction. That is to say, from point D, we will do perpendicular on AB. Again, from point D, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. Likewise, we do another construction, that is to say, from point C, we will draw perpendicular on AB. Again, from point C, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. Because of the fact that ABCD is a trapezoid, and a trapezoid is a quadrilateral with one pair of parallel sides. In trapezoid ABCD, side DC is parallel to side AB. And again, in trapezoid ABCD, side DC is parallel to side AB. Those two angles are defined as one-sided interangles, and they are located between the parallel lines DC and AB. And therefore, according to Rule 17, the sum of those two one-sided interangles must be equal to 180 degrees. So I think from Rule 17, according to Rule 17, the sum of one-sided interangles that are located between two parallel lines is equal to 180 degrees. In the drawing, we have line A that is parallel to line B, line C has those two parallel lines A and B, and those two angles are defined, alpha and beta are defined as one-sided interangles. And because of the fact that those two one-sided interangles, alpha and beta, are located between the parallel lines A and B, the sum of those two one-sided interangles must be equal to 180 degrees according to this rule, Rule 17. That is to say, alpha plus beta equals to 180 degrees. Likewise, those two angles 1 and 2 are defined as one-sided interangles and are located between the parallel lines A and B. And therefore, the sum of those two angles must be equal to 180 degrees. That is to say, angle 1 plus angle 2 equals to 180 degrees according to this rule, Rule 17. So we can actually implement Rule 17 in our drawing. Why? Because in our drawing, as I already mentioned, we have those two one-sided interangles that are located between the parallel lines DC and AB. And therefore, the sum of those two one-sided interangles must be equal to 180 degrees. So we have here, this is a right angle, this is to say this is equal to 90 degrees in its size, plus this missing angle, that is angle DCJ. In total, the sum of those two one-sided interangles must be equal to 180 degrees according to Rule 17. Here we subtract 90 degrees from this equation, and we get that the missing angle DCJ is equal to 180 degrees minus 90 degrees is 90 degrees. So actually, this is the missing angle DCJ that equals to 90 degrees in its size. Likewise, those two angles are defined as one-sided interangles and are located between the parallel lines DC and AB. And therefore, according to Rule 17, the sum of those two one-sided interangles must be equal to 180 degrees. So this is a right angle plus this missing angle, this is actually angle CDN. In total, the sum of those two one-sided interangles must be equal to 180 degrees according to Rule 17. Here we subtract 90 degrees from the equation, and we get that the size of the missing angle CDN is equal to 180 degrees minus 90 degrees is 90 degrees. Okay, this is the missing angle CDN that is equal to 90 degrees in its size. So actually in quadrangle DCJN, in this quadrangle we have 4 rectangles, and therefore quadrangle DCJN is a rectangle according to rule 5. So I want to know, this is the big quadrangle DCJN, that is a rectangle according to rule 5 because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So, in the big rectangle DCJN, side DC must be equal to the opposite side JN, but DC is 32, therefore the opposite side JN must be also equal to 32 units in its length. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that side CJ is equal to the opposite side DN. So, those two right angles are similar to each other, can relate to each other according to side rule. So, I'll explain why those two right angles, triangle DAN and this triangle CJB, can relate to each other. First of all, the hypotenuses of those two right angles, they are both equal to 41 units, and therefore they are equal to each other. In addition, those two sides are the two opposite sides of rectangle DCJN, and therefore they are equal to each other. And finally, those two sides are equal to each other also. I'll explain why those two sides are equal to each other. So I copied these two right angles in a new page and we implemented the Pythagoras theorem on this on those two right angles. Those are the two right angles that are going to the original drawing. We define the length of side DN as x and the length of the hypotenuse DA as y. So in this right angle DNA, according to the Pythagoras theorem, x squared plus an squared equals to y squared. Again, x squared plus na squared equals to y squared. X squared plus an squared equals to y squared. Here you subtract x squared from this equation and you get that an squared equals to y squared minus x squared. Here we took out of this equation and found out that an, the missing side an, equals to the square root of y squared minus x squared. Likewise, we did the same operation here. We implemented the Pythagoras theorem on this right triangle CJB. Cj equals to Qn, and Qn equals to x, and therefore Cj must be also equal to x. The hypotenuses of those two right triangles are equal to each other. And because of the fact that QA equals to y, then CB must be also equal to y. So in this right triangle CJB, according to the Pythagoras theorem, y squared, that is the square of the hypotenuse, equals to x squared plus jb squared. Read again. Y squared equals to x squared plus jb squared. Here we subtracted x squared from this equation and finally found out that jb squared equals to y squared minus x squared. Here we took out of this equation and finally found out that the missing side jb equals to the square root of y squared minus x squared. So both those sides an and jb, they are both equal to the square root of y squared minus x squared, and therefore they are equal to each other. That is to say, an equals to jb. So in those two right angles, all the sides are equal to each other. those two sides are both equal to y, therefore they're equal to each other. Those two sides are both equal to x, therefore they're equal to each other. And side AN equals to side JB. Therefore, those two right angles can go into each other according to side rule. And again, I should prove that those two right angles can go into each other according to side rule. So, write it down. Actually, I found out that the right angle CJB congruent, this is the sign of congruent, to the right angle DNA, according to angle and according to side rule. And from the fact that those two right angles can go into each other, we will derive that side AN in the right angle DNA is equal to side JB in the right angle CJB. So write it down. AN equals to JB. AN equals to JB according to the rule that corresponding sides and congruent angles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides, that is to say AN and JB, must be equal to each other. AN equals to JB, so if we define AN is x, then JB must be also equal to x. So we define AN is x, and therefore JB must be also equal to x. AB in total equals to 50 units, according to what is given in the question. So AB equals to x plus 32 plus x. AB equals to x plus 32 plus x. And AB equals to 50. So 50 equals to x plus x is 2x plus 32. 50 equals to 2x plus 32. Here we subtract 32 from the equation, and we get that 50 minus 42 is 18. So 18 equals to 2x. We will divide this equation by 2, and finally we get that x equals to 18 over 2 is 9. So x equals to 9 units in its name. So side AN equals to x, and x equals to 9 units. Likewise, side JB also equals to x, and x equals to 9 units in its name. In the next step, I will copy the right angle CJB in a new page, and we will implement the Pythagoras theorem on this right angle CJB. Side CJ is the missing side. Side JB equals to x, and x equals to 9 units in its length. And the hypotenuse CB equals to 41 units in its length, according to what is given in the question. CB equals to 41. According to the Pythagoras theorem, in this right angle CJB, here by PT is the abbreviation for Pythagoras theorem. So according to the Pythagoras theorem, in this right angle CJB, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared. That is 1681. And it is equal to CJ squared. CJ is the missing side, so we leave it as it is. So it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, it is 81. So in total we should find out that 1681 equals to CJ squared plus 81. Here we'll subtract 81 from this equation, and you get that CJ squared equals to 1681 minus 81 is 1600. So CJ squared equals to 1600. Here we take out all this equation, and finally we get that the missing side CJ equals to the square root of 1600, that is 40. So the missing side CJ equals to 40 units in its length. This is the missing side CJ, that equals to 40 units in its length. Our task is to find out the area of this trapezoid ABCD. In the beginning of the lecture, I presented to you the formula for the area of any trapezoid. The area of any trapezoid equals to the sum of its two parallel bases. In this case it is DC plus AB. Times the height over 2. The height is CJ because it's greater than 90 degrees with the two parallel bases. So this times CJ over 2. And again, the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is to say DC plus AB, times the height CJ over 2. DC is 32 plus AB. AB is 50 times the height CJ. We just right now found out that CJ equals to 40 divided by 2. So in total, we found out that the area of trapezoid ABCD, that is the area that we are looking for in this question, it is equal to 32 plus 50 times 40 over 2. 40 over 2 is 20. So in total, this expression equals to 32 plus 50 is 82 times 20. 82 times 20 is 1640 square units. And that is the answer to the question. I repeat again, I should found out that the area that we are looking for this question, that is the area of this trapezoid ABCD, is equal to 1640 square units. So finish with the first question. In the next step, I'll present to you the second question, and we'll solve the second question by using two different methods. In the second question, our task is to find out the area of this quadrilateral ABCD. So in the drawing we have quadrilateral ABCD. This is angle ABC, this is right angle. This is angle ADC, this is also right angle. This is angle BCD, this is equals to 45 degrees in size. Side DC equals to 25 units in its length. This is side AB, that is equal to 10 units in its length. Repeat again, our task is to find out the area of this quadrilateral ABCD. So, first of all, we will do a construction. That is to say, from point B, we will draw perpendicular on DC. Again, from point B, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B and DC. This point is point K. In the next step, we will do another construction. That is to say, from point A, we will draw perpendicular on BK. Again, from point A, we will draw perpendicular on BK. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BK. This point is point T. By doing this construction, we can do the quadrilateral ATKD. Inside quadrilateral ATKD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this 4 missing angle must be equal to 90 degrees in its size. So inside quadrilateral ATKD we have 4 right angles, and therefore according to rule 5 we can relate to quadrilateral ATKD is a right angle, because it has 4 right angles. So written down, this is quadrilateral ATKD, this is a rectangle according to rule 5. We will define the length of side AT from the rectangle ATKD as A. We know that the opposite sides of a rectangle are equal to each other. So in rectangle AT DK, side AT equals to the opposite side DK. But AT is A, therefore the opposite side DK must be also equal to A units in its length. What is the length of the missing 9 segment KC? KC equals to DC minus DK. Again, KC equals to DC minus DK. So write it down. KC equals to DC minus DK. So KC in total equals to DC is 25 according to what is given as the question, minus DK. DK is A. So in total KC equals to 25 minus A units in its length. This is 97 KC, this is equals to 25 minus A units in its length. In the next step, we'll focus on the right triangle BKC. This is the right triangle BKC. In the right triangle BKC, this angle equals to 90 degrees inside, this angle equals to 45 degrees inside, and therefore this first missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. We have the rule that in front of equal angles in the triangle are equal sides. So if we focus on the right triangle BKC, in front of those two equal angles, we have those two sides that must be also equal to each other. But side k is equals to 25 minus a, therefore side bk must be also equal to 25 minus a units in its length. This is side bk, that is equals to 25 minus a units in its length. The big angle ABC equals to 90 degrees in its size. This is angle KBC, that is equals to 45 degrees in size, and therefore this missing angle must be equal to 90 degrees minus 45 degrees, that is 45 degrees. So angle ABK is equal to 45 degrees in its size. In the right small triangle ABT, this angle equals to 45 degrees. This angle equals to 90 degrees, and therefore this first missing angle must be equals to 45 degrees in its size, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So, in the right small triangle ABT, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side AT equals to A, therefore side BT must be also equal to A units in its length. Side BT equals to A units in its length. What is the length of side TK? From the drawing, it is very easy to see that TK equals to BK minus BT. Again, BK minus BT equals to TK. So it is known TK equals to BK minus BT. So TK equals to BK. BK is 25 minus A minus BT. BT is A. So TK in total equals to 25 minus A minus A, that is 25 minus 2A. 25 minus 2A units in its length. So TK equals to 25 minus 2A. So it is known. This is 97 TK. This is equals to 25 minus 2A units in its length. In rectangle ATKD, the opposite sides are equal to each other. That is to say, side TK is equal to the opposite side AD, but TK is 25 minus 2A, therefore the opposite side AD must be also equal to 25 minus 2A units in its length. So AD equals to 25 minus 2A units in its length. Now, it is very easy to see, to find out the area of quadrilateral ABCD, but before that, we'll implement the Pythagoras theorem on this right small triangle ABT. So copy the right small triangle ABT in a new page, and we will implement on it the Pythagoras theorem. Here by PT is the progression for Pythagoras theorem. Summary. This is the right triangle ABT. This is according from the original domain. This right triangle ABT according to the Pythagoras theorem. BA squared, this is the square of the hypotenuse, equals to BT squared plus AT squared. Then again, BA squared equals to BT squared plus AT squared. So as you know, BA squared, this is the square of the hypotenuse, equals to BT squared plus AT squared. BA is 10, therefore BA squared is 10 squared, that is 100. And it is equals to BT squared. BT is 8, therefore BT squared is 8 squared. Plus 80 squared. 80 is 8, therefore 80 squared is 8 squared. So now if you found out that 100 equals to 8 squared plus 8 squared. 8 squared plus 8 squared is 2a squared. So 100 equals to 2a squared. Our task is to find out the area of this quadrilateral ABCD. So, first of all, quadrilateral ABKD is a trapezoid. Why? Because of the fact that in rectangle ATKD, side TK is parallel to the opposite side AD. And again, rectangle ATKD, side AD is parallel to the opposite side TK. But TK is part of the straight line BK. Again, TK is part of the straight line BK. Why BK is a straight line? Because angle BTK equals to 90 degrees plus 90 degrees, it is 180 degrees. And any angle that is equal to 180 degrees in size, it is defined as a straight line. So BK is a straight line, and TK is part of the straight line BK. And you know that if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore, in total, we can say that BK is parallel to AD, and therefore, in quadrilateral ABKD, we have one pair of parallel sides. Side BK is parallel to the opposite side AD. And therefore, quadrilateral ABKD is the trapezoid. So, as you know, quadrilateral ABKD is a trapezoid because it has one pair of parallel sides. Side BK is parallel to the opposite side AD. And what is the area of trapezoid ABKD? The area of trapezoid ABKD is equal to the sum of its two parallel sides, that is to say BK plus AD, times the height 80. 80 is the height because it has 90 degrees with the two parallel bases. So times the height 80 over 2. So if you found out that the area of this trapezoid ABKD, in total it is equal to BK plus AD, that is the sum of its two parallel sides, times the height 80 over 2. BK equals to 25 units in its length, plus AD. AD equals to 25 minus 2a units in its length. Times 80, 80 equals to a divided by 2. So in total we should find out that the area of this trapezoid ABKD equals to BK, that is 25 minus A, plus AD, that is 25 minus 2A, times 80, that is A over 2. Here we have 25 plus 25 is 50, and minus 8 minus 2A is minus 3A. So in total, in the numerator we have 50 minus 3A times A divided by 2. Here we'll open the brackets and we get that 50 times A is 50A, minus 3A times A is minus 3A squared divided by 2. So in total we should find out that the area of trapezoid ABKD is equal to 50A minus 3A squared over 2. So until now, in the new page, that the area of trapezoid ABKD is equal to 50A minus 3A squared over 2. Again, we should find out that the area of trapezoid ABKD is equal to 58 minus 3A squared over 2. Our task is to find out the area of this quadrilateral ABKD. From the drawing, it is very easy to see that the area of quadrilateral ABCD in total is equal to the area of trapezoid ABKD plus the area of this right triangle BKC. Again, the area of this big quadrilateral ABCD in total equals to the area of this trapezoid ABKD plus the area of this right triangle BKC. So write it down. The area of the big quadrilateral ABCD in total it is equal to the area of trapezoid ABKD plus the area of this right triangle BKC plus the area of the right triangle BKC. We have already found out that the area of trapezoid ABKD equals to 50A minus 3A squared divided by 2 minus the area of the right triangle BKC. The area of the right triangle BKC equals to the base KC times the height KB over 2. Repeat again, the area of the right triangle BKC equals to the base KC times the height KB over 2. So in total, the area of trapezoid the area of quadrilateral ABCD equals to 50A minus 3A squared, and we have KC. KC equals to 25 minus A times KB. KB also equals to 25 minus A, so it is 25 minus A squared divided by 2. So in total, the area of the quadrilateral ABCD equals to 58 minus 3A squared plus 25 minus A squared divided by 2. So it is 50a minus 3a squared plus 25 minus a squared. 25 minus a squared equals to 25 squared, that is 625, plus a squared minus 2 times 25 times 8, that is minus 50a, divided by 2. Here 58 minus 50a is 0, so those two expressions will get cancelled. And we're left with minus 3a squared plus a squared is minus 2a squared plus 625 divided by 2. So total we found out that the area of quadrilateral ABCD equals to 625 minus 2a squared over 2. But we already found out that 2a squared equals to 100. So we can substitute 2a squared in this equation by 100. And we get that the area of the quadrilateral ABCD equals to 625 minus 2a squared. 2a squared is 100, so it is minus 100 divided by 2. 625 minus 100 is 525 divided by 2. And again, we found out that the area of this big quadrilateral ABCD equals to 525 divided over 2. 525 over 2 is 262.5 square units in its size. And again, we should find out that the area that we are looking for this question, that is the area of this big quadrilateral ABCD is equal to 262.5 square units in its size. So we finish with the first method of the second question. In the next step, I will present to you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we will do a construction. That is to say, we will extend side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. And we will define the touching point of the extended side DA with the extended side CB. This point is point M. By doing this construction, we created the big right angle MDC. This is the big right angle MDC. In the big right angle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this fat missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So, in the big right angle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side DC equals to 25 units in its length, therefore side MD must be also equal to 25 units in its length. So MD or DM equals to 25 units in its length. MC is the hypotenuse of the right triangle MDC. So MC is a hypotenuse, it is absolute straight line. So if you focus on the lower side of the straight line MC at point B, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 said that the sum of the areas on one side of the straight line is equal to 180 degrees. So which areas we have at the lower side of the straight line MC at point B? We have this angle that is the right angle plus this missing angle. The total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right small triangle A and B, this angle equals to 45 degrees. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size, according to the third rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the right small triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But AB is 10, therefore MB must be also equal to 10 units in its length. It is very easy to see that the area of this quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of the small right triangle AMB. Again, the area of this quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of this small right triangle AMB. So write it down. We actually found out that the area of this quadrilateral ABCD is equal to the area of the big right triangle MDC minus the area of this small right triangle MBA. Repeat again. The area of quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times the height DM over 2. The area of the big right triangle MDC equals to the base DC times the height MD over 2 minus the area of the small right triangle MBA. The area of this small right triangle MBA equals to the base AB times the height BM over 2. Again, repeat again, the area of the small right triangle MBA equals to the base AB times the height BM over 2. DC is 25 times MD is also 25, so it is 25 squared divided by 2 minus AB is 10 and BM is also 10, so it is 10 times 10 so in total we found out that the area of quadrilateral ABCD equals to 25 squared, that is 625, minus 10 squared, that is 100, divided by 2. 625 minus 100 is 525, divided by 2. 525 over 2 is 262.5 square units in its size. So in both methods, we found out that the area of this quadrilateral ABCD is equal to 262.5 square units in its size. We finish with the second method of the second question. So in the next step, I will start the lecture. We'll start with the first question, of course. In the first question, our task was to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. ABCD is a quadrilateral because it has four sides, and because of the fact that side DC is parallel to side AB, this quadrilateral ABCD is defined as a trapezoid. This is trapezoid ABCD. Side AB is parallel to side DC, and therefore it is a trapezoid. If we define the length of side DC as A and the length of side AB is B, then the area of trapezoid ABCD equals to the sum of its two parallel sides, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees with two bases. So the area of trapezoid ABCD equals to the sum of its two parallel sides, that is A plus B, times the height edge over 2. So, first of all, we implemented rule 2 in our drawing. So, application of rule 2, according to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, circle, this is the common external point, point P. From this common external point, point P, we have two tangents to this circle. Tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because if we focus on this common external point, point D, from this common external point, point D, we have two tangents to this circle. Tangent DA, tangent DK, and tangent DE. And according to rule 2, they are equal to each other. That is to say, DE equals to DK. If we define the length of tangent DE as A, then the length of tangent DK must be also equal to A because they are equal to each other according to rule 2. Likewise, if we focus on this common external point, point C, from this common external point, point C, we have two tangents to this circle. Tangent CE and tangent CF. And according to rule 2, they are equal to each other. That is to say, CE equals to CF. So if we define the length of tangent CE as C, then the length of tangent CF must be also equal to C because they are equal to each other according to rule 2. Likewise, we focus on this common external point, point B. From this common external point, point B, we have two tangents to this circle. Tangent BL and tangent BF. And according to rule 2, they are equal to each other. That is to say, BF equals to BL. So if we define the length of tangent BF as B, then if we define the length of tangent BF as D, then the length of tangent BL must be also equal to D because they are equal to each other according to rule 2. And finally, if we focus on this common external point, point A, from this common external point, point A, we have two tangents to this circle. Tangent AK and tangent AL. And according to rule 2, they are equal to each other. So if we define the length of tangent AK is B, then the length of tangent AL must be also equal to B according to rule 2. What is the length of side DA plus the opposite side CB? CA plus CB equals in total to A plus B plus C plus D. Say it again. DA plus CB equals to A plus B plus C plus D. What is the length of CD plus AB? CD plus AB in total equals to A plus B plus C plus D. And again, CD plus AB also equals to A plus B plus C plus D. And because of the fact that those two expressions they are both equal to A plus B plus C plus D, that means that they are equal to each other. That is to say, DA plus CB equals to CD plus BA. CD is the missing side, so it is AB is 50, DA is 41, CB is also 41. 41 plus 41 is 82. So CD plus 50 equals to 82. Here we subtracted 50 from the equation and find out that the missing side CD equals to 82 minus 50 is 32. So this is the missing side CD that is equals to 32 units in its length. In the next step, we did a construction, that is to say, from point D we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. The next step we did another construction, that is to say, from point C we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. We know that ABCD is a trapezoid, and trapezoid ABCD, side DC is parallel to side AB. Those two angles are defined as one-sided interangles and are located between the parallel lines DC and AB. And therefore, the sum of those two angles in total they must be equal to 180 degrees according to Rule 17. This angle equals to 90 degrees plus this missing angle in total they must be equal to 180 degrees, and therefore this missing angle must be equal to 90 degrees in its size. Likewise, those two angles are also defined as one-sided interangles and are located between the parallel lines DC and AB. And therefore, the sum of those two angles in total they must be equal to 180 degrees. This angle is a right angle. 90 degrees plus this missing angle in total they must be equal to 180 degrees, and therefore this missing angle must be equal to 90 degrees in its size. So in total we should find out that in quadrangle DCJN we have 4 right angles, and therefore quadrangle DCJN is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DCJN, side DC must be equal to the opposite side JN, but DC is 32, therefore the opposite side JN must be also equal to 32 units in its length. Likewise, in the same rectangle, according to the same rule, side DN must be equal to the opposite side DC. So those two sides are equal to each other. So if we focus on the right triangle DNA and this right triangle DJB, we have those two sides are equal to each other, and the hypotenuse CB is equal to the hypotenuse DA. This third missing side must be equal to this third missing side, according to the Pythagoras theorem. So I actually copied those two right triangles in a new page, and I proved that those two sides are equal to each other. So actually, those are the two right triangles that are coming from the original domain. We define the length of the hypotenuse DA is y, and the length of the one side DN is x. Here also the hypotenuse CB equals to y because they are equal to each other, and side CJ also equals to x because they are equal to each other. So in this right triangle DNA, according to the Pythagoras theorem, y squared equals to x squared plus na squared. Again, y squared equals to x squared plus an squared. Here we subtract x squared from the equation, and we found out that an squared equals to y squared minus x squared. Here we took out of the equation, and we found out that the missing side an equals to the square root of y squared minus x squared. Here, according to the Pythagoras theorem, y squared equals to x squared plus jb squared. Again, y squared equals to x squared plus jb squared. Here we subtract x squared from the equation, and we found out that jb squared equals to y squared minus x squared. Here we took out of the equation, and we found out that jb equals to the square root of y squared minus x squared. So AN and JB, they are both equal to the square root of y square minus x square, and therefore they are equal to each other. That is to say, AN equals to JB. So therefore, those two right angles can go into each other according to side rule. Those two sides are both equal to x, therefore they are equal to each other. Those two sides are both equal to y, therefore they are equal to each other. And we just like to found out that AN equals to JB. And therefore, those two right angles can go into each other according to side rule. And again, we found out that the right angle CJB congruent, this is the same congruent to the right angle DNA according to a side rule. From the fact that those two right angles can go into each other, we derive that side AN of the right angle DNA is equal to side JB of the right angle CJB. According to the rule that corresponding sides and congruent angles are equal to each other. Those two right angles can go into each other, and therefore those two corresponding sides, AN and JB, must be also equal to each other. So AN equals to JB. So if we define the f of AN is x, then JB must be also equal to x. AB in total equals to 50, according to what is given in the question. So 50 equals to x plus 32 plus x. AB equals to 15, AB in total equals to x plus 32 plus x. AB is 50, so 50 equals to x plus x is 2x plus 32. Here we subtracted 32 from this equation, and we found out that 50 minus 32 is 18, so 18 equals to 2x. Here we divided this equation by 2, and we found out that x equals to 9. So AN is equals to x equals to 9, and JB is equals to x equals to 9. In the next step, I copied the right angle CJB in an equation and implemented on this right angle CJB the Pythagoras theorem. This is the right angle CJB that I copied from the original domain. According to the Pythagoras theorem, this right angle CJB, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 681, and it is equals to CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total, we found out that 1681 equals to CJ squared plus 81. Here we subtracted 81 from this equation, and we found out that CJ squared equals to 1681 minus 81 is 1600. So CJ squared equals to 1600. Here we took a root out of this equation, and we found out that the missing side CJ equals to the square root of 1600, that is 40. This is the missing side CJ, this equals to 40 units in its length. Our task is to find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually DC plus AB, times the height CJ over 2. And again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is DC plus AB, times the height CJ over 2. Why the height is CJ? Because the height CJ creates 90 degrees with 52 bases. So the area of trapezoid ABCD equals to the sum of its two parallel bases, that is DC plus AB, times the height CJ over 2. DC is 32, AB is 50, CJ is 40, divided by 2. 40 over 2 is 20, and 32 plus 50 is 82. So in total, the area of trapezoid ABCD equals to 82 times 20, that is 1640 square units in size. So in total, we found out that the area of this trapezoid ABCD equals to 1640 square units in its size. So we finish with the first question. In the next step, I presented to you the second question, and we solve the second question. We're using two different methods. In the second question, our task is to find out the area of this big quadrangle ABCD. So in the drawing, we have quadrangle ABCD. This is angle ABC, this is right angle. This is angle ADC, this is also a right angle. This is angle BCD, this is equals to 45 degrees in size. This is side DC, this is equals to 25 units in its length. This is side AB, this is equals to 10 units in its length. Again, our test is to find out the area of this big quadrangle ABCD. So first of all, we did a construction, that is to say, from point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point K. In the next step, we did another construction, that is to say, from point A, we draw perpendicular on BK. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BK. This point is point T. By doing this construction, we're going to do quadrilateral ATKD. Inside quadrilateral ATKD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the side of this 4 pieces again, total must be equal to 360 degrees. According to the rule, the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces again must be equal to 90 degrees in size. So inside quadrilateral ATKD, we have 4 right angles, and therefore quadrilateral ATKD is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ATKD, we define side AT as A. So side AT must be equal to the opposite side DK. But AT is A, therefore the opposite side DK must be also equal to a unit in its length. What is the length of this missing side KC? KC equals to DC minus DK. Again, KC equals to DC minus DK. So KC equals to DC, that is 25, minus DK, that is 8. So in total, KC equals to 25 minus 8 units in its length. In the next step, we focus on this big right triangle BKC. On the big right triangle BKC, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first angle must be equal to 45 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the right triangle KBC, in front of those two equal angles, we have those two sides that must be equal to each other and their lengths. But KC is 25 minus 8, therefore BK must be also equal to 25 minus 8 units in its length. We have the big angle ABC equals to 90 degrees in its size. This angle equals to 45 degrees, and therefore this missing angle must be equal to 90 degrees minus 45 degrees, that is 45 degrees. So in the small right triangle ABT, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this front missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle ABT, in front of those two equal angles, we have those two sides that must be equal to each other and their lengths. But side AT equals to 8, therefore side BT must be also equal to a units in its length. What is the length of TK? TK equals to BK minus BT. Again, TK equals to BK minus BT. So TK equals to BK, that is 25 minus 8, minus TK minus BT, that is A. So in total, TK equals to 25 minus 8 minus 8, that is 25 minus 2A. This is the missing side DK, that is equals to 25 minus 2 units in its length. In rectangle ATKD, side TK must be equal to the opposite side AD. But TK is 25 minus 2A, therefore the opposite side AD must be also equal to 25 minus 2A units in its length. In the next step, we implemented the Pythagoras theorem on this right triangle ABT. So I covered the right triangle ABT in the new page, and we implemented the Pythagoras theorem in this right triangle ABT. This is the right triangle ABT that I covered from the original drawing. In this right triangle ABT, according to the Pythagoras theorem, AB square or BA square, that is the square of the hypotenuse, equals to BT square plus CA square. BA is 10, therefore BA square is 10 squared, that is 100, and it is equals to BT square. BT is 8, therefore BT square is 8 square, plus 80 square. 80 is 8, therefore 80 square is 8 square. So in total, 100 equals to 8 square plus 8 square, that is 2A square. So 100 equals to 2A square. In the next step, I prove that quadrilateral ABKD is a trapezoid. Why quadrilateral ABKD is a trapezoid? First of all, in rectangle ATKD, side TK is parallel to side AD. But TK is part of the straight line BK. Why BK is the straight line? Because this angle is 180 degrees, and any angle is equal to 180 degrees in its size, it must be a straight line. So BK is a straight line. So part of the straight line BK, that is TK, is parallel to DA. Therefore, the straight line itself, BK, must be also parallel to AD. and because of the fact that in quadrilateral ABKD, side BK is parallel to the opposite side AD, quadrilateral ABKD is defined as a trapezoid, because it has one pair of parallel sides. BK is parallel to AD. So we have trapezoid ABKD. What is the area of this trapezoid ABKD? According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABKD equals to the sum of its two parallel bases. This is BK plus AD times the height TA over 2. Again, the area of trapezoid ABKD equals to the sum of its two parallel bases. That is BK plus AD times the height AT over 2. BK is 25 minus A, plus AD is 25 minus 2A, times AT, this is A, divided by 2. 25 plus 25 is 50, minus A minus 2A is minus 3A, times A, divided by 2. We open the brackets here and found out actually that 50A minus 3A squared over 2 is equal to the area of trapezoid ABKD. And again, we found out the area of this trapezoid ABKD equals to 58 minus 3A squared over 2. Okay, again, we should find out that the area of trapezoid ABKD equals to 58 minus 3A squared over 2. But we have already found out that 2A squared equals to 100. Actually, we have here the area of trapezoid ABKD equals to 58 minus 3A squared over 2. And our task is to find out the area of this trapezoid, the area of quadrilateral ABCD. It is very easy to see that the area of quadrilateral ABCD equals to the area of trapezoid ABKD plus the area of this right triangle BKC. But again, the area of trapezoid ABCD in total equals to the area of trapezoid ABKD plus the area of the right triangle BKD. The area of trapezoid ABKD is equal to 58 minus 3A squared over 2 plus the area of the right triangle BKC. The area of this right triangle BKC equals to the base KC times the height KB over 2. Repeat again, the area of the right triangle BKC equals to the base KC times the height KB over 2. So the area of quadrilateral ABCD in total equals to 58 minus 3A squared. KC is 25 minus A, BK is also 25 minus A, so it is 25 minus A squared divided by 2. We open the brackets and we found out that 58 minus 3A squared equals to plus 25 minus A squared. 25 minus A squared equals to 25 squared, that is 625, plus A squared minus 2 times 25 times 8, that is minus 58 divided by 2. 58 minus 58 is 0, so those two expressions will get cancelled. And we left only with minus 3A squared plus A squared is minus 2A squared plus 625. Or 625 minus 2A squared over 2 is the area of quadrilateral ABCD. But we already found out that 2A squared equals to 100. So we can substitute 2A squared by 100 and get that this expression in total equals to 625 minus 2A squared. And 2A squared is 100 divided by 2. So total the area of the quadrilateral ABCD equals to 625 minus 100 over 2. 625 minus 100 is 525 over 2. So if you found out that the area of this big quadrilateral ABCD, in total it is equal to 525 over 2, that is 262.5 square meters in size. So we finish with the first method. In the next step I presented to you how to find out the area of this trapezoid ABCD. We actually did the construction, that is to say we extended side DA and side CB by straight line until they touch each other and define their touching point. This point is point M. By doing this construction, we're going to do the right big triangle MDC. In the right big triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this first angle must be equal to 45 degrees in its size. According to the rule that the sum of the angles in a triangle is equal to 180 degrees. So in the right triangle MDC, in front of those two equal angles, we have those two sides that must be equal to each other and their lengths. But side DC is 25, therefore side MD must be also equal to 25 units in its length. MC is the hypotenuse of the right triangle MDC, so MC is hypotenuse, it is absolutely a straight line. So if you focus on the lower side of the straight line MC at point B, the sum of the angles must be equal to 180 degrees according to all three. All three says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the lower side of MC at point B? We have this angle, that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle MBA, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this first angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. So in the right small triangle MBA, in front of those two equal angles, we have those two sides that must be equal to each other in their lengths. But AB is 10, therefore MB must be also equal to 10. The area of quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of this small right triangle MBA. And again, the area of quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times the height MD over 2. The base DC times the height MD over 2. Minus the area of this small right triangle MBA. The area of this small right triangle MBA equals to the base AB times the height MB over 2. This is the base AB times the height BM over 2. DC is 25, MD is also 25, so it is 25 squared, that is 625. Minus 10 times 10, that is 100. 625 minus 100 is 525 over 2. So in total, we should find out in both methods that the area of this quadrilateral ABCD equals to 262.5 square units in its size. Okay, thank you very much.